Hi everybody, I have just created this PowerPoint slide as a way of giving you an overview of confounding, the concept of confounding, drawing on information from the book, and also just giving you additional examples to help you as you wrestle through this concept of what are variables that could cause confusion in my data, and what is this concept of confounding. So the first question is, what is a confounder? And a confounder, put simply, is really just a third variable that messes up, confuses, confounds the relationship that you're looking at. So we talk about an exposure like smoking and an outcome like cardiovascular disease. I'm going to use that example to illustrate some key concepts about confounding. A confounder is first and foremost associated with the exposure. It has to also be associated with the outcome, but it can't be caused by the exposure or caused by the outcome. And if it is caused by the exposure, that puts it on the pathway that we consider to be the causal pathway. It explains the reason why the association occurs. This slide shows the concept of the confounding triangle, and that is that at the base of the triangle is the relationship you're looking at, the exposure in relation to the outcome, which you think is a causal relationship, but there's a third variable that might be creating that relationship, so confusing it by generating a relationship that doesn't exist, or it might actually obscure the real relationship. The most important thing to remember is that the triangle is such that if the confounder is not associated with the exposure and the outcome, it's not a confounder, because it can't create an association between the two unless it's connected to them both. So it has to be associated with both the exposure and the outcome. So even if you can imagine something that's strongly related to your outcome, unless you can imagine that it's equally related to your exposure, then it can't be a confounder. A confounder creates a false relationship, which means in this example, coffee is only a confounder if people who drink coffee tend to smoke. That's relating to the association between smoking and coffee drinking. And also if coffee causes or is associated with cardiovascular disease. If coffee is associated with smoking and also causes cardiovascular disease, it could cause the appearance of a relationship between smoking and cardiovascular disease, even if it doesn't actually occur. So this broken arrow here between smoking and cardiovascular disease is a relationship that is not real, but it's caused or contributed to by the fact that smoking and coffee drinking are associated with each other. The other way around is that maybe there really is a relationship between smoking and cardiovascular disease, but if, for example, coffee drinking actually prevents cardiovascular disease, then if smoking and coffee drinking are associated with each other, it would work against the appearance of this relationship. So there might really be a relationship, but because people who are smoking are also drinking coffee, it takes away, it looks like there is no association. So it takes away the real effect. In the above example, coffee drinking actually acts to obscure the true relationship. So it confounds by obscuring. And just to reiterate, the confounder has to be associated with both. And if coffee drinking is not associated with smoking and also cardiovascular disease, it can't be a confounder because it can't create that false association. So this blue arrow is an example of a false association that is created between smoking and cardiovascular disease when the real relationship is the coffee drinking. And I'm just scrolling back to the previous example where you can see the atherosclerosis itself is an intermediate on the pathway because there is an arrow going from smoking. So if you have an arrow pointing either from the exposure or from the outcome to your confounder, then it's breaking either the rule of being an intermediate on the pathway or this rule of that it can't be a consequence of the outcome. So put differently, we have these rules that to be a confounder, it has to be associated with the exposure, has to be associated with the outcome. It can't be just associated with one or the other. It has to be both. And that it can't be caused by the exposure or caused by the outcome. And the sort of 3 is repeated twice because if it's caused by the exposure, then it breaks the rule that it can't be on the pathway. So it can't be the reason why the association occurs. In the rest of the presentation here, I'm going to show you not just the concept of what is confounding, but literally how to test for confounding using the data that we have on COVID-19 at the county level in Illinois. Because in Illinois, we have information not just at the county level, but we have information on age, ethnicity, and sex. So I'm going to show this example comparing Rock Island County versus Henry County. And these are 2 counties with very different demographics in terms of the population. And they also have very different risks in terms of COVID-19. So we're going to look and see to what extent is that potentially confounded or explained by ethnic differences. So remember, a confounder is associated with the exposure. So that is ethnicity is different in Rock Island County versus Henry County. It's also associated with the outcome. Ethnicity is very much related to COVID-19 because of multiple layers of structural racism. It is not caused by the exposure, so obviously being in one county or another is not causing ethnicity, and it's not on the pathway. It's not the explanation why the association occurs. Now somebody might say, well, the reason why Rock Island County and Henry County are different is because of the ethnic differences. If that's the rationale for looking at ethnicity, in that case we would say it's not a confounder. Now, personally, I'm interested to see whether the Rock Island and Henry County are different independent of ethnicity. So I want to take that ethnicity issue out of the equation. So first, what you want to know is that stratifying is a concept of breaking that big risk ratio, that crude, that rough risk ratio, where you just throw everyone in Rock Island, everyone in Henry County together into one comparison. You have a risk ratio of 3, it's a rough estimate. Once you stratify into groups related to your confounder, you're breaking any association with that confounder. In other words, if there are differences according to ethnicity in Rock Island and Henry County, you can break that relationship by separating the ethnic groups into categories and getting separate risk ratios. Now, before I go further, it's really important to say that ethnicity is really poorly measured. It doesn't really mean a whole lot. It's a rough estimate of a concept of structural racism, of access to care, of differences in occupation. It sort of throws everything into one soup. So it's poorly measured variable. It doesn't relate to how people identify themselves. And these are responses based on the census. So I've roughly categorized them into people who responded self-identifying as white and all the other ethnic groups which don't belong together in one group. But for the sake of simplicity and because Henry County is 95% white, there really wasn't an option to break it further down. So I just wanted to give that caveat because when it comes to bias and misclassification, we can talk about that concept at the end of the term. How do we know whether something qualifies as a confounder? So there is sort of a rule of thumb that we use in epidemiology, and that is once we stratify into the 2 different groups and we have stratified risk ratios and we want to compare those to that rough, everything thrown in together crude risk ratio at the top is that difference in the risk ratio is greater than 10%. Now in this case, I'm going to give an example where the original crude risk ratio is 3, and after breaking it into the two stratified groups, the two strata, we have risk ratios of 2 and 2. So I'm just giving a simple example where the two risk ratios after adjusting for stratifying for ethnicity, you have a difference between the original 3 and the final 2. And so here we would say our adjusted risk ratio is 2 after controlling for ethnicity. And we can say that there's confounding because by that rule of 10%, the original 3 goes down to 2. That's a change of 33% in the risk ratio. So here, giving a different example where the risk ratio isn't changed that much. So going down from 3, if you stratify and you get a 2.8, it really doesn't qualify as a greater than 10% change. So one of the things you can do, instead of calculating that difference, you can also just take your risk ratio and say, what is 10% of that risk ratio? So the lower bound would mean it goes down below 2.7, and the upper bound would mean that it goes greater than 3.3. So depending on how you're comfortable doing the measurement, you can look at this 10% change in different ways. One is to actually measure the percent change in your estimate, or to get a ballpark by looking at the 10% boundaries around 3.0, the original risk ratio, to see where it hits the mark of being greater than 10%. So in this example, I'm just showing you that you might do stratified analysis and you might see there is no confounding. It changes a little bit, but not really enough to matter. That original 3.0 was close enough to give us an estimate. And you don't want every tiny difference to be classified as confounding because you lose power every time you stratify. So this is something that you'll find as you go through 2 or 3 variables. Imagine if you have a second layer. So you have this first layer, and then let's say you had to stratify yet again. So each of these groups, the white and non-white stratified group, would then be stratified further by male-female. So everything would be divided in half again. So the more things that you add into your model, the less power you have statistically, and the smaller the numbers get in each of your cells, so it becomes less reliable. So here we're going to start with the crude risk ratio. This is real data taken on June 7, 2020 from Rock Island County and Henry County, taken from the Illinois Department of Public Health website. So we had 715 cases so far of COVID-19 Rock Island County. We also have a population size of 147,546 based on county census data. And so that number is taken from a different site. It's not on the public health website. It's taken from the census data website. That link is also in Blackboard. So what is the risk of getting COVID-19? Well, that's a probability based on the number of COVID cases divided by the population size. So that's 0.00484. That's the risk of having tested positive for COVID-19 for those living in Rock Island County. Now, that risk is a lot higher than it is in Henry County. So it's not just the COVID case numbers that are smaller or not lower in Henry County, but the population size is also quite small. So proportionately, the risk of COVID-19 in Henry County is only 0.00139. And so taken as a ratio, you can see that Rock Island County is 3.5 times greater than the risk in Henry County. So how are we going to use this information to measure confounding? Well, we need to stratify the results by ethnicity. But we have a bit of a problem. Once we broke the results into the different strata, so looking at the non-white or the multiple ethnic groups combined together and those who self-identified as white, what we find is a number of COVID cases did not identify in either group or did not feel comfortable answering the question. So if we add the white and non-white categories together, for Rock Island County, you get 574 instead of 715. So we're missing a lot of people there. And in Henry County, we're also missing some. Originally, there were 70 COVID cases, but once you take into account ethnicity, you have 64. So a lot of people are not replying to that question for various reasons, potentially. And we need to be able to compare our crude risk ratio to our stratified risk ratios directly. They have to be the same people in the boxes. So in order to get a crude risk ratio that is truly broken into these two stratified groups, we are recombining the white ethnicity with the non-white groups and adding those into the risk groups. Now, another weird thing you're going to see is if you were to add up the sample size of the individuals identifying in the non-white categories of ethnicity and those who self-identified as white, it would add up to a number that's greater than the population size for the county. Well, what that means is some people are identifying with multiple ethnicities. That makes sense. A lot of people identify with more than one ethnic group. So they will essentially be double counted if we were to add their numbers. So I'm holding the population size to be the maximum level, which is the total population for the county, but I am reducing the number of COVID cases to reflect the people who actually gave an answer for ethnicity and didn't leave that information blank. So taking only those who gave information on ethnicity, we have a new risk ratio, which is 3.1, reflecting the fact that fewer people in the COVID cases identified or reported one of the ethnic groups. However, of those who did answer the question, and we can stratify based on white or other groups, non-white, we're sort of throwing them together, we find that the results go from 3.1 to somewhere between 1.9 and 2.5. Now, when you're doing the test for confounding, one question might arise: which stratified risk ratio should I choose? If the two risk ratios are similar, or if they're both greater than 10% different from the crude, it won't matter. So the question is whether the two stratified risk ratios are different from each other and whether or not it matters which one you choose. If they're really different from each other, then you will probably want to use that to test next week for effect modification. So look for, when you do the stratified risk ratios, look for examples where the two risk ratios are really different from each other. Choose the one that's the most different for next week when you do effect modification. Now, you might find that all of your stratified results show very different numbers, like this one, 1.9, 2.5, that's different enough to question. So you might not have any confounding, but even so, select one of these stratified results to test for confounding just to show understanding for this week's assignment. So even in the example I gave, I suspect maybe there's some effect modification because 1.9 and 2.5 are really different from each other. But still, I'm going to show through the example of how you would look at this as a confounder. So I'm going to start with that crude risk ratio. That's 3.1 comparing Rock Island to Henry County. And that's just using the people who actually reported an ethnicity. So taking out all the people who left that number blank. And the stratified risk ratios are 2.5 and 1.9. And I'm going to take that 2.5 and I'm going to say, what is the proportion or this percent difference between that 2.5 and the original 3.1? How big is that difference? And if it's a greater than 10% difference between the original, the crude, the 3.1, and the adjusted, the 2.5, then we talk about confounding. So that 3.1, we're going to subtract the 2.5, and we're going to divide it then over the 3.1 to get the difference as a proportion of the original number, and then multiplying that by 100 to get the percent difference. So if you do that calculation, you'll see that there's a 19% difference between the stratified risk ratio. So the risk ratio for whites is an even greater difference. So that is a much greater than 10% difference between the stratified risk ratio, so both of them are going to be greater than 10%, and the original crude risk ratio. So in the example that I've given, we found confounding. The stratified results are greater than 10% different from the crude. That shows confounding. The risk ratio of 3.1, that original crude, we call it risk ratio, even accounting for just the people who responded on ethnicity, that 3.1 still doesn't tell us the whole story. When we stratify or adjust for ethnicity, it gets us closer to what the true risk ratio may be. And what we see is that risk ratio is attenuated. It's less strong. It's closer to 1. So it goes down from 3.1 to 2.5 or even as low as 1.9. So that 3.1 risk ratio is what we'll call confounded by the ethnic differences between Rock Island County and Henry County. And this confounding in the relationship could be explained by structural racism, differences in access to health care, exposure to risk at work, and a greater need for culturally diverse health communication. So the fact that we see evidence of confounding means that triangle exists. It means that there is an association not just between ethnicity and the county, but also between ethnicity and the outcome, COVID-19. Now, the final thing is you're going to be wondering perhaps, what is the difference between confounding and effect modification? So confounding is what we've just tested, and you might have seen differences between your two strata, and I said, well, think about maybe testing if you see that the risk ratio is really different between, for example, men and women, or between two different ethnic groups. If you compare them, you might look at the concept of effect modification, and that is where we go back to that concept of the causal pie. What effect modification will be testing, what we're going to look at next week, is this idea that in addition to county of residence, some other factor may be working together with county of residence to amplify the effect. So that would be something you might see when you look at two stratified results and they're really different from each other because one is more amplified than the other is. And that is exactly what we're going to look at next week. You might see some, like the example I gave, where even though the crude and the stratified results are different enough to talk about confounding, the two stratified results are different enough from each other that you still have a question. Is it a confounder? Is it an effect modifier? And in many cases, when you look at data, it's not a clear-cut example. So the more examples you see and look at, the more you can really think through these concepts of confounding and effect modification. But confounding is the concept you're looking at your stratified results and you're comparing them to your original crude result when they're put together. And effect modification is the idea that if the risk ratio is really different between the two separate stratified groups, it says that they're really behaving differently, that maybe there is that additional causal pie, and we can test that using a method that we're going to explore next week.